we have discussed about the possibility of how we can simplify our data sets, or how we can reduce dimensions in a specific, let's say, domain or in a specific problem by doing the diagonalization. The diagonalization, if we're talking about a matrix which is a square matrix, we use eigenvectors. If the system or if the matrix is not a square one, what we do is that we can have a vector, a matrix which is 7 by 3. What we can do is that we can, from this matrix 7 by 3, we can multiply with its transpose, and we'll have the 7 by 3 times another matrix B, which is 3 by 7, and we're going to get a matrix C, which is 7 by 7, and then we can also do the A transpose, which is 3 by 7 times A itself, which is 7 by 3. This is C, which is 3 by 3. Now, what we see here is that because of the symmetry, or something that which we can prove, we have that if we multiply any matrix with its transpose, the result will be symmetric. So this matrix C, which is 7 by 7, let me write this one S1, just that I want to say that this is a symmetric matrix. And symmetric matrices, they are nice matrices to work with because the eigenvalues, they are all real numbers, okay? So they are real numbers, and if they are real numbers, then this makes these diagonalizable, okay? Because sometimes we might get some roots of the as eigenvalues, and the roots will be the roots of the characteristic polynomial of a specific matrix. If they are complex numbers, then the matrix, it might not even be diagonalizable. So if we go back to the basis of linear algebra, this is something perfect because we get a matrix which is symmetric, S1 or S2. The size is different. The eigenvalues are real, and the problem is diagonalizable. So somehow, but then when we find the eigenvalues, so for a moment, let's not forget, we can find here the eigenvalues, which will belong the eigenvalues of C. But these eigenvalues of C, they have a relationship with the sigma values, sigma 1, sigma 2, sigma 3, which are the singular value decomposition of the matrix A initially. And now this matrix A, which can be 7 by 3, this can be written as three matrices, U, sigma, and V transpose, where the U, this is a rotational matrix, this is also a rotational matrix, and since they are rotational matrices, we know that V transpose is equal to V inverse, and then this matrix here, the sigma, is a square matrix, which is having here sigma 1, sigma 2, sigma 3, and so on, and this is all zeros. And any system that has a dominant axis or a dominant axis, we can say that the sigma 1 will be larger than sigma 2. And these systems which have a dominant axis, they can be data sets, that can be described like this, okay? So if we have a data set which is spread in space or in any domain or in any n-dimensional space, it can be 4-dimensional space. How do you do that? You have a 4 by 4 matrix. This is what constitutes a 4-dimensional space. Here, it is easy for us to distinguish a dominant axis because this could be our respective sigma 1, this could be our sigma 2, okay? So in this case, we can see how the two major axes can be different. At the same time, we can have another data set, but now the data set might be distributed like this. Again, we can easily distinguish one of the major axes, which is this, okay? And the other major axis is going to be the following. So for these two cases, we can easily find the major axis, and what is important is to figure out what is the ratio between sigma 1 and sigma 2. It looks like here the ratio of sigma 1 over sigma 2 is much larger than 1, okay? We're just assuming, but here the ratio between sigma 1 and sigma 2 is just larger than 1. But now we have a problem. If we have a new data set where the spread of the data is like this, it is so random that we cannot easily distinguish two major axes to represent the data. Now, we are working on a whiteboard, of course, and that's why we are talking about two major axes. So this would be one of the major axes which describe the system. But this is not the only one. This is also acceptable, so I'm drawing this in black. And I can also draw, this is also acceptable, okay? Because we can find an infinite number of coordinate system to describe or to span the R square. So it is somewhat equivalent to having a coordinate system that looks like a Cartesian coordinate system here, or we can draw another coordinate system that is going to look like this, okay? But when the data set is distributed like which is completely random, like in a circle, then it is clear to all of us, based on on the symmetry, that here in this case, our sigma 1 over sigma 2 is equal to what? This is going to be 1. Not exactly 1, because randomness is always there, but it's close to 1. And depending on the size of the problem, if you have like 3 data points and you randomly generate into a 2-dimensional space, this sigma 1 over sigma 2, it might be a large number. But if we increase the number of points from 3 to 30 or 300 or 3000, then the randomness is so much, then later on, this sigma 1 and sigma 2 will be close to each other. They will be equal to 1. And then we have also mentioned before that if the data set is not in 2D, but let's say 5D, which could be a matrix which is 5 by 5, then assuming that sigma 1 is always larger than sigma 2, and this is larger than sigma 3, larger than sigma 4, and larger than sigma 5, okay? And assuming that if the data is too random, but it's not, well, the number of data sets should be 10,000, I don't know. I mean, I've tried this one before. If you randomly generate 10,000 or 100,000 data points, then you start to see this not equal, but this is approximately. So then, assuming that this is the smallest, I asked a question in the previous session. We said that if this is the case, what is, for a random data set, what is sigma 5? Or what percentage of the weight is on the 5th dimension? So maybe I can correct my previous question. What percentage of the weight is in this element or in this dimension? Because we said the last time that the weight that is in the first sigma, it is described as sigma 1 divided by the summation of all the sigma I, okay? This is the weight or the energy that is stored in the first sigma. The reason that we use the energy, it is that energy is a scalar quantity, and it's a good term to use. So it has remained in the literature like that. Now, then, sometimes to reproduce a data set, based also on the examples we covered in the previous sessions, we might have that the data set might not have all the weight on one sigma, but also in the first 2 sigmas. So then the weight on the first 2 sigmas, it can be described as sigma 1 plus sigma 2 over the summation of all of the sigmas. So, but then, so this is what we mean with the weight. And these numbers that might come up in here, if you go over the slides that we have shared, you might get numbers which are something like this. Here we can get 75% of the weight might be located only in the first sigma. Then it might jump immediately to 98% in the first 2 sigmas. Then the sigma 3, it can be, in principle, this is going to be very few percent. Maybe this is the summation of all the sigma I. Here in sigma 3, for data sets which have a pattern, okay, and data sets that have a pattern, you can pick up the pattern from the sigma 1 and sigma 2, which are much larger than the rest. Imagine if this has less than 1%. This discussion here is for general data. Now, if we go back to the original question, if the data is very random, what could be the weight on the sigma 5? Or what is the maximum possible value? What is maximum of sigma phi? Would you have any suggestion? Any suggestion here? So the maximum weight that can be allocated to sigma 5, it is expected to be around 20%, okay? Because it cannot pass 20%, because the best thing that can happen is that this will be all equal to each other, but that's a very small possibility again, unless the number converges to infinity. Only then you can get it. But numbers in the order of 10,000 might see a convergence to this value of 20%. Okay, so this is again a small reminder regarding the use of sigmas when we try to figure out the weight on the major axis or on the dominant axis. And often what we might see is that the dimensionality reduction is a very useful approach that can be used to simplify very complex problems. And in essence, the dimensionality reduction, what it is trying to figure out the axes which have very little weight. So since they are ordered in an SVD decomposition, so in any singular value decomposition, in any case like this, then the sigmas which are at the rock bottom, how can I say, the last values of sigmas, if those have a small weight, you can immediately say that the problem that you are given, you can reduce the dimension or you can simplify. Now, regarding the independent component analysis, what this technique is trying to do, this is trying to separate two different data sets from each other. And this is done by trying, so similar to this diagrams that we have here, we may assume if we have, let's say, now we're talking about separating two different signals. We might have, let's say, a data set that looks like this and a data set that looks like this. Here, independent component analysis can distinguish the different features because it can select a dominant axis along this way and another dominant axis in this way. So it is, if the data set is projected and has a similarity like this, they can be completely separated. So let's consider that this is, maybe it's best if we draw this one in red. So this is signal S1 and this is signal S2. And the objective is that we want to separate them completely from each other, given a convolution of these two signals, or given a summation of these two data sets. Second, okay. Okay, but now if the signal S1, if this one in itself, it looks like this, if it is very random. Now we are drawing a similarity with this case, and if S1 is a different data set, but it has no major axis, then it is imperative that it would be very difficult for any user to clearly separate these two data, okay, the S1 from S2. So now, and in order to be able to separate these, there is a it's a useful mathematical apparatus which is used in order to extract two different data sets. And the major component that is used is the statistical data, and this is not the correct word. The statistical analysis of the data, statistical analysis of the data. And regarding the statistical analysis of the data that is relevant, it will be the histograms. So we might have a look at so the simplest way to report this one is we have to look at the histograms of a certain data. And the histograms, what they do reveal, they reveal the first moment, the second moment, the third moment, and the fourth moment. The first moment on a data set, we define this one as the average, okay? So this is, if we have a data set where we can have the following: x is equal to 1, -3, 4, 7, 9. Okay, so here we have a certain data set. And then the first moment here is the average of all of these values. Okay, so the first one is average. The second moment of the data is the standard deviation. Standard deviation. The third moment, it is skewness. The fourth moment is kurtosis. So there are these measures which make us possible. It makes possible for us to completely separate two different data sets. Now, the average, we know the formula of the average. Formula of the average, it's sum of xi divided by n. Then the standard deviation, the formula, it's let's write here the standard deviation. It is xi minus x average, all squared. And then what do we do next? I think we take the square root. Okay. So this would be the standard deviation. Then the skewness, it has a generalized formula which also helps us to determine whether a histogram, so its skewness is different from 0 if we have distributions that are like this. So if we have a histogram where the length from the right side is not equal to the length from the left side, if they're not equal, then we have a skewness which is larger than 0 or smaller than 0. Kurtosis is another measure which truncates or elongates more than possible a Gaussian distribution. So imagine if we have a Gaussian distribution which is beautifully described like this, a non-zero kurtosis means a truncation, which means a cutoff of some tip, or a more than normal elongation. So these two graphs in black, they show two different data distribution which have kurtosis different from 0. There are more moments regarding the data set which distinguish more detailed information regarding the data distribution. Now, often we are lucky that unless the cases where the data are completely random, even the randomness it can be defined in different ways. So most of the time, the data that we have, they are not Gaussian or they are not normal distributed. So the data, they are not normally distributed, or we can say they are not Gaussian distributed. And this is a good news, because if the data is not normally distributed, then we can. It is easy for us to pick up essential elements of which or from which we can go further and try to separate them. And regarding these, actually, we're going to see an example here, and the example that we're going to see will be how we can mix two different images, and these two different images we want to do singular value decomposition. So here we have one image which we can have a tree, and here we have another image where we have a vehicle. Okay, and then we want to figure out. So we want to add them together. So we want to add them, and then we might get here, we have a tree, but then in front of the tree, we have this vehicle. So now, what we'll do is that we will be given this data, and then we'll try to figure out that this data is composed of the mixture of these two different images. Now, the mixing and the separating of images, this is a it's one of the relatively difficult problems because it is obvious that the mixture of the data set or the mixture of the pixel intensities at one specific location in the coordinates of the matrix, this is a complex problem. But we can solve this one, and we are going to talk here about the major tools that are used. And we have to show actually what is the path, how this is normally done. But then, if this is possible for a two-dimensional data, then one can also argue that if we have two signals which are one-dimensional data, and how could these two signals be defined? So we can have, let's say, for example, let's assume we have a signal which is from electroencephalography, which is the data that are collected from different regions of the brain. Those graphs, if somebody, only if you are the specialist, they have good readout of these graphs. But let's imagine that we have a signal which might be coming, I don't know how the signals could look like, but let's say that you have an electrode located here, and the signal might include some features. Then you have another signal which is collected, let's say, from a sensor which you might have at the back of your head, and this graph could also be looking like something different. Then if you add these two, and then we look at the total graph, and it might be this peak, which is modified by this high frequency down here, and maybe we can get this. So again, the problem, it will be defined as before. To a user, we can give this graph, and the question, it will be the following. Find for us, what is the first signal here, and what is the second signal? Which in principle, this means that try to separate the signals which are gathered from this electrode and also probably from this other electrode. Now, we said that the theory, it's provided for us, it is, and we can work with it. It works to some acceptable levels, even for images, which is two-dimensional signals, which are also discrete. So if we are good here, most probably you can do something good also in here. Now, there is a tool which might be a little odd, which is used when we do this analysis, which is the following. So, and actually, when we talk about the standard deviation, we have the standard deviation, the sigma. Let me write this one, the standard deviation. This is the square root of variance, okay? So this is the square root of variance. But what is the variance? The variance, var, this is equal to the summation of xi minus x average. So this is the x average, all squared. Okay, so this is the variance. And it looks like the variance is it never has negative terms, so it's always a number which keeps increasing. But now we have another value, which is covariance. The covariance, let me denote it like this. It tells it's a measure of the correlation coefficient between two different data. So the covariance, let's have a look, for example. And covariance, actually, we have discussed this one when we did, if you go over the lecture notes in the previous sessions, we used to have, let me think for a moment. Just a small reminder, I just can go back for a moment, just to remind you. We had matrices which were, let's say, 3 by 7, and in the original domain, before doing the singular value decomposition, we had a covariance matrix in the coordinates x. But after we do this, after we multiply this one with its own transpose, we can go to a new domain where the covariance in the new variable y, we have most of the values in the covariance matrix, or let me call it this way, the Okay. Sorry, I had a fluctuation in the internet connection. Sorry about that. Can you hear me?
Yes.
Yes.
So,
Yes.
yeah, notice that I was expecting for it to come back. So now this is how we describe the variance, okay? And then if we take the square root, we find the standard deviation. But now we have another definition, which is very similar to the variance, which is called the covariance. And covariance is equal to xi minus x average times yi minus y average, with a bar we denote the average. And this covariance, if we divide the covariance by the sigma x and the sigma y, we get the correlation coefficient. Okay, so two signals that correlate with respect to each other, we can figure out whether they correlate by looking at this expression. So the variance and covariance, this is square. So imagine for a moment, if x is measured in meters, we have for the variance is measured in meters squared. Similarly, if x and y, they are both in meters, we notice that also covariance has a unit of x meter squared. So the dimensional analysis, it helps us a lot. So for a moment, let's assume that we have these points as they are shown here. So let's have here 1.5 to 3, and at 4 we have 3. So here we have 4 points, okay, 4 data points. What are these points? We have x is 1, 2, 3, and 4. We will not do this in detail. And this is x. And here we have the y. And the y is located at 1. This is 0.5. This is 1.5. And here we have a value of 3. So the question is here, how can we find what is the covariance? So we immediately, what we do, we find the average. Here we have 5 plus 5. This is 10. Here we have 2, 3, 6, okay? This is the sum. The average is 10 divided by 4, this is 2.5. 6 divided by 4, this is 1.5. And then the covariance here, it is equal to x1 minus x average, which is here 1 minus 2.5 times 1, because this is y1, minus 1.5, okay? And then allow me to use the board a little. So then we sum over the second point, it's 2 minus 2.5 times 0.5 minus 1.5, okay? Plus the other point is 3 minus 2.5 times 1.5 minus 1.5, plus these numbers, I try to make them up randomly. 4 minus 2.5, 3 minus 1.5. So this is the covariance, okay? And then we have a look at the calculations. We see here that this is this is equal to minus 1.5 times, so what, let's see, this is minus 1.5 times minus 0.5 plus, so if you have a calculator, or you can do this a little faster than me, then here we have 2.5, this is minus 0.5 times minus 1, wait a second, this is minus 1, plus 3 minus 2.5, this is 0.5 times 0, okay, this factor is cancelled out, plus 1.5 times 1.5. So in the end, we find a number, and this number, this is something like, this is plus 1.5 divided by 2, this is 0.75, so I can write it here, 0.75, and we need from a different angle, 0.25, this is plus 0.50, 1.5 times 1.5, we get 3 over 2.
2.25.
What is this?
2.25.
You mean this one?
Yes.
Okay, and the total number, it looks like we get a number like 5, 4, 1, 3.45, okay. So we get 3.45 here. Then we have to look for what is this correlation coefficient. So how do we do that? So we have this number 3.45. We have to figure out what is the sigma in x. Now, what is the sigma in x? If we look here, we don't have a lot of data, but the sigma in x, it's going to be a graph which is going to look like this. Okay, and we need a value here, which I don't know. We need to calculate it using this expression, and let's not do it now. But this has a distribution which I'm trying to do it randomly. This might be something like 0.8. Let's assume this is or 1 point something, and then the distribution, the sigma, this is sigma x. Okay, this is sigma x, and the data in y. Where are those? Those are the domain of y values. They are from here to here. With 4 data points, you cannot construct much statistical analysis, but the data distribution is going to look something like this. So the sigma x, sorry, the sigma y, which will be found from the histogram down here, this is sigma y, we can calculate these two values, and then we have this 3.45 divided by these numbers, we can get the correlation coefficient. Now, if two variables, they correlate together, and correlation is defined as they increase at the same time and they decrease at the same time, okay? So this is what we mean with correlation. And in principle, let's now look at as if we have one vector here and one vector here. In essence, so this is variance, standard deviation, good covariance is like very close in principle to the variance. Now, when we have the images, what is often done is that one image, which is, let's say, a matrix which is 5 by 5, of course, 5 by 5, we don't have much information, right? This is going to be 500 by 500. But let's assume that this is 5 by 5, and this ends up to be also 5 by 5. What we do is that this image, which is 5 by 5, we convert it into a vector, okay, which is 25 by 1. So we just reshape this whole image, and it's something which we can not understand it, okay, because it's a vector. How can you read a line and figure out that you are talking about a tree? That's not the case. Then also similarly, you have a vehicle here, described in a matrix which traditionally is 500 by 500, but let's assume it's 5 by 5. We make this one also a vector. When you say a vector, we just put the pixel values 25 by 1. And then what we can do in this case is, in fact, or let's say it this way, if we have two different trees, and then we represent two images of a tree here and a tree in a different mountain, you make these two images as a vector, you find the correlation coefficient, you're going to find a large correlation, okay? The statistical analysis can pick it up. Now, similarly, if we calculate the vector which we obtain from reshaping the 5 by 5 matrix into a vector 25 by 1, so reshaping this in a vector and reshaping this into a vector, and trying to find the correlation coefficient, as we did in here, using this expression, then we are going to find a smaller correlation between the vector of a tree and the vector of a vehicle. And with vectors, we are just talking about the reshaping of a square looking like or a rectangular image or a rectangular data set. Now, this is something which we have not seen it yet. So these data sets, they can be converted into vectors, and then these vectors, maybe it's best if we go over the code, that we can show it from here. I can share a few more words actually, because trying to do the independent component analysis, I want to remind you also how the general picture really is. So now we talked about the statistical analysis here, which we want to say a few more words in the future sessions. But as a reminder, the singular value decomposition, what it does is that it is any matrix A, which is U sigma times V transpose. So this means that we can have a data set which is shown here. Then the first step is that we rotate it. So this one is rotated into here. Then we multiply by sigma, which means that we can elongate this axis and let's assume that so this is the sigma factor. So we're changing the relative projection along a major axis, and here we have another rotation, okay? So this is the V transpose. So we have these three operations, and the essence that we need to do is, in fact, try to figure out what is this angle of rotation. So this is tricky, or this is essential. So we have here a matrix. Wait a second. This is also a rotational matrix U. This is also a rotational matrix V. So we need to find out what are these two angles. Okay. So whenever we work with a data set, in essence, we are going to see these. Okay. Now let's try allow. So let's assume for a moment that, wait a second. So let's say that we want to mix two images as they are shown here. And here we see some flowers, a couple of flowers, and a garden side. And then in order to mix those, what we can do, first we read the images, okay? And then we just want to see how they look like, and then we make up a mixing matrix. The mixing matrix, it can be a 2x2 matrix, which is going to come up with a mixture of the first two to get a new one, and with another combination of these two images to come with another other image. So if we have a look at this matrix A is composed of 4 divided by 5, and beta, which is 1 divided by 5, and then half and 2/3. So it's the first row, it's 4 divided by 5 is 0.8 and 0.2. The second row, it's 0.5 and 0.66. So this is as we see here, let's not forget that this is a matrix, S1 and S2, they are just the images. Since we want to add those, these images should be the same dimension, because addition of two matrices, it is defined only for equal dimensions. So if you want to do this one later, you need to have two equal ones. Then we mix those and we obtain X1 and X2, which are two different images, which are going to look like this. So this one is made up by picking up 80% of the yellow flowers and 20% of the garden picture. And the second image at the bottom right side of the screen, it's composed by getting 33% of the flowers and 67% of the garden image. Now, they are not, here we make an argument that these are not the best images to mix and try to separate those. What would be reasonable is, for example, trying to pick up the apartments in Tirana. You know that Edirama has colored them with different features, so no two of those are the same. So if you pick two pictures of one apartment or you can get Palati Meshigieta with another one, those two could be very good choices. I mean, images of different apartments in Tirana city could be separable, but these are not the best images to separate. Now, if we change the beta, we see that now the mixture is different from what we see here. So the bottom left side image, it's a lot of flower, the bottom side. Here there is less flower, more garden, because we have changed the beta function, okay? The top ones are the original images. Now, what we try to determine initially are the angles which we try to draw. We draw them also on the figure on the board, because we said that when we're trying to determine what are these major axes, we need to find or to extract some possible direction of the angle which has a maximum variance. So if you remember, if we have elliptical distribution of data, there is always one larger axis with larger variance than the other orthogonal one. So this is the mixing of the images up to the half of the graph. Then immediately we see here a capital X1 and capital X2 somewhere in the middle of the slide, where this X1, which is a square image, we convert it into a vector. Okay, so this is what I was saying before. So we reshape it into a dimension m by 1, which is m is the number of rows, n is the number of columns. We multiply those two, and we create two vectors. And then once we find these two vectors, we find the x1 will be equal to x minus the mean. So here we find the deviations of each pixel from the mean. And at the same time, we find also the deviations of each pixel in image x2 from the mean of that image. So you have the image of a tree, you calculate the average of all the pixels, and you subtract it from everything. And then in here, we try to determine, the angle theta, and this angle theta is described as the inner product of x1 by x2. So this inner product, we see it here as wait a second, so this is the product of these two. Now the expression is a little more complex. I need to use a board for this one, but you can, I'll need, after we finish the presentation here, we can pass on the board. Then after we find this theta, we can immediately construct the rotational matrix US, which is the USV. This is the first rotation, and we know that rotational matrices, they are always cosine sine minus sine cosine. Okay, this is how we describe those. And this would be the rotation matrix. Now the angle that we find here, at least what I found, is that we find an angle of 45 degrees, and the rotational matrix for a 45-degree angle, this is what it comes up to be, because cosine and sine, they are equal. Now, this was the first step, trying to determine what was the angle. The second step, we try to calculate what are the sigmas. Now, this sigma 1 and sigma 2, they correspond to the variance along two major axes. In order to find these, well, you can see this expression. So we calculate x1 times cosine theta plus x2 times sine theta. This is all squared. So this is the variance. But at the same time, this is somewhat the projection of these two vectors. And let's not forget, these are not exactly the vectors. These are the deviation, because it was overwritten. All the values of the pixels, they were substituted by the values of the deviations of each pixel from the mean. So here we can find sigma 1 and sigma 2. One thing which is essential mathematically is here that the theta 1 or theta 0 that we consider, this is going to define one of the axes, and we are considering the other axis as theta 0 minus pi over 2, okay? So we are assuming that we have an orthogonal coordinate system over which we can define the rotation of the matrices. So we try to define, actually, I'm afraid I've made a mistake here, because I find that one of the sigmas is almost 0. So 10 to the power minus 23, this is very small, but I have to double check this again later. And I notice that I have one of the sigmas only on a single axis. So this is not correct, or maybe when I copy pasted the output of the graphs, this is what I obtained. Okay, I even wrote a note here. So there seems to be a problem. The first theta was 45. The two sigmas were significantly different. One was too small, one was too large. Okay, so, but I think I figured out where the problem is. In fact, I can show you in the code. So here, I think the problem was here. If you see this line, x2 is equal to reshape, I've reshaped x1 again onto x2. But in the code, I fixed that, so that problem is gone. But I just left it here because you can have a look at and see how things can go wrong for some little mistakes. And just by looking at this result, this is almost unacceptable, because we cannot have the two mixed images that you saw, flowers plus the garden side, to be so, what's the name? So independent with respect to each other, or putting all the weight on one sigma. Now, okay, so I corrected this part of the code, and I found another angle which is equal to minus 39 degrees. The rotational matrix is slightly different. This is how it should have been. And the sigmas now are comparable. So we're not talking anymore sigma 1 and sigma 2, one being 0, the other one was extreme value. So let's see how we had here. Sigmas, one was 10 to the power 11, the other one was 0. Here, they are more comparable with respect to each other. So we found the angle which corresponds to the rotational matrix U. We found the sigmas in the matrix sigma. Now we need to find another angle in the V, okay? So step 3 is here. This US1, etc. So wait a second. So I need to use the board actually to show here, but the line 1, 2, 3, 4, 5, line 5 and 6, this is the expression which finds the angle phi from an inverse tangent between the second moments of the data. So now, initially, we use the averages to pick up or to distinguish a specific difference in the histograms of the images. So on the board, we draw histograms, and we said that we can distinguish two different histograms by looking at the sigma, standard deviation. But then we can pick up the second moment, and this second moment is shown here, and try to maximize and again, what was the moments? The moments, it means that the average of the data, the standard deviation, the skewness, the kurtosis, etc. So now we try to find the angle phi 0 using the line 5 and 6 in this slide by trying to maximize the difference between the skewness of two different histograms, which in principle correspond to two vectors where we have determined the deviations. Okay, after we find the angle, we find the rotational matrix V, which is still composed of cosine, sine, minus sine, cosine. And so we find the last angle, the angle that I found, it's 6.8 degrees. Now, this was the description of the code line by line, and the original images are at the top, the mixed images are in the middle of the slide, and the separated images, and we don't see a very good success rate, but it's not bad. It might be acceptable for some applications or for some images with completely different structure, because the major issue here is with the image which has the flowers, because the flowers, they are almost Gaussian, okay? They are almost random. So we want some features in there so that we can easily separate them from each other. And now, if we come here, all we might need to do is, in fact, so again, this is where we read the images, we plot those, then we can determine a specific value for beta, which will be in the mixing matrix. And this is evaluate selection. Now here, so the mixing of these two images, this is how it's going to look like. And then we try to see what are the sizes of x1, which x1 actually we can see is 400 by 500, and they are both RGB images, color images. And then what we do is that we reshape them, we make them vectors, and after we make them vectors, I think it's good to go over the code to understand actually how we can describe in a discrete manner what the analytical expressions ask from us. So, okay, so I think we looked at this part. This is where we made them vectors. Then this is the part where we subtract the mean. And now the capital X and capital Y, they are, as it's written here, they are deviations from the mean. Then using, trying to maximize the difference between the means here, we determine the angle theta 0, which is arctangent of a calculation that we report here. Then once we find the angle theta 0, we write the rotational matrix, which is going to be composed of cosine, sine, minus sine, cosine. And actually, now I even have a little doubt. I'm afraid that mund duket kur gjem të rotational matrix, sikur minus sinusi është diku lart, po shikojeni pak, mund ta kem unë gabim, se mua personalisht po m'pëlqen shumë. Te rotational matrix, kjo minus sinusi, a është këtu poshtë apo është lart? Is it in the first row?
For një sekond, sepse kam te kisha te prezantimi rotational matrix, duhet ta kem direkt këtu. Sa të hapet pak.
Unë mbaj mend që minusi është te rrjeshti i parë.
Minusi është rreshti i parë, yes. Cosinus minus sinus, sinus cosinus.
Atëherë bie që kjo matricë që kam këtu, me të vërtetë unë po e shoh, po s'po m'pëlqen, që ka gabim atëherë. Nëse ju mund E keni të kodin të slide-et, mund ta bëni run, but I don't want to change it now, okay? Por me të vërtet që nga bim kjo minusi këtu, do të jetë minusi këtu para we can do it, we can see what we can get. Okay. Pastaj hapi dytë është ajo që patëm që diskutuam pak te slide-et, thamë që we can find the variance of the along one direction, and this would be the variance in the other direction, because, and we can see the sigma 2 is related to the reprojecting the data not along the angle theta 0, but along the angle which is 90 degrees with respect to this, so it's minus pi over 2. And step 3 finds, it does the reorganization of the data and finds the other rotation, the angle which represents the final rotation. And then, in the end, what we try to obtain is that we try to obtain these separated images. And then, if we have some accepted level of separation of the images for discrete images for discrete data sets, such as an image, we might get better results if we have vectors, or let's say signals like electroencephalography, for example. If they're coming from two different features, we can test whether the SVD is a good separator between two signals, okay? But this is how the independent component analysis works if we want to use the tricks provided by the eigenvalues and the eigenvectors. Do you have any question regarding this material? Okay, so now I want to share also with you some notes I have regarding the statistical analysis of data. I'm going to share with you in the Google Classroom. But regarding this part of ICA, this is all I wanted to go over. A ka ndonjë pyetje, ndonjë gjë tjetër që mund të diskutojmë? Pyetje lidhur me materialin kryesisht? If not, wait a second. Eagerly joined. Okay. Okay, we can stop this session.